Okay, so now we will build a matrix for parallel beam tomographic measurement. For parallel beam tomographic measurement. This is a simple method based on the use of the radon Matlab's there surely are more effective ways to do it. Okay. So let's choose the size of the unknown. The image has size 2 to the j times 2 to the j. Let's denote n equals so here let's take j first to be, let's say, like 8 and n equals 2 to the. Okay, so now we have that. Then choose angles for projections. Yep. Okay, yeah, I was. I'm good. Yeah, I was very worried about my arithmetic skills, but if you agree, I mean, yeah, please correct me if it's wrong. Never trust a professor. So the angles, they are usually given by degrees, I think, for the radon function. So we could take, let's put it this way, number of angles is something. Let's say here it's 33, for example. Let's add here I think odd is better, because then there won't be exactly the same directions twice, I think, if I'm not mistaken. Well, we'll see. Let's take number of angles, and then let's take, or actually let's do it this way. So we'll go from 0 to number of angles minus 1. So here we have now integers from 0 to n minus 1. So we have n numbers there, and let's multiply 360 divided by n. I think this should give us kind of sparse sampling of the full circle. Then let's specify, let's find out the eventual size matrix A. Namely, the size is k times n, where n is as above the dimension of the unknown vector f, and k is the number of X-rays. The number of X-rays depends on Matlab's inner workings. So let's just use radon once here. Let me call it the temporary sinogram. Let's apply radon to zeros of size n by n. Oh, well, let's do it that way. And angles. So this will give us a dummy sinogram of only 0 values, but it will have the same size than the sinograms to follow. And then we can take k is length of temporary sinogram dropped as a vector. So now we can record how big our matrix A eventually in the end should be. Then we can initialize our matrix. And to save space, let's do it as in sparse format, because there will be a lot of zeros in our final matrix A, because you know every X-ray is only intersecting so many pixels, not all of them. So mostly the values in A matrix will be 0. So we'll do it sparse. So A equals I think it works like this. We have Kn. Let's check this. Okay, so we are actually using this one, so we will have just a 0 sparse max. Yes?
It makes a stupid question, but wasn't n the total number of pixels?
Yes, n is the total number of pixels.
And we're doing zeros n times n there.
Yes. Oh, sorry, yes. Oh, that's right. Yes. Yes. So we should have. Excellent. This would have been. Yeah, much better.
Now it's like 60.
Ah. Maybe this is. Let's start with j being a smaller one. So now it's, I think, 8 by 8.
Yeah, should be.
Should be. Thank you.
Shouldn't you have now it's easier also to j?
So 2 to the power of j times 2 to the power of j.
Yes. Ah, getting better all the time.
I'm sorry, while you're correcting things, maybe you want to also change the length.
Length. Yes. Extreme programming in action. How about now? Let's try to run this for just to see if it works. Okay, no errors. Excellent debugging before the actual fact. Good. So then construct matrix A column by column. This is a computationally wasteful but we'll just do it. So, well, how many columns are there? I think n. Construct unit vector. Let's say I unit vector unit vector. So this would be zeros of the size we want f to be, like this, and we put 1, 1 in it. And Matlab automatically does this when I have a matrix, but I'm using just one index to enter the matrix. It will go by the numbering we want to use. Then apply radon. So we can do this. So maybe we can do it just like this. A. So what do we have? We should have a column number I equals. Oh, maybe we have to do it in a couple of steps. Actually, I think we can use this temp thing even here, but not this one. Now we should have this unit vec like this, and then let's move also this temp vector to be sparse. Maybe it works already with this. Let's see. As I have said many times, I think in mathematical programming it's a very good idea to check what's going on visually once in a while, almost all the time. Let's do spy A, which will show us the non-zero elements in A. Ooh. Okay. Yes. We need to drop it as a vector, not the sinogram form. Okay. Here we have something, and maybe we could even let's do this step by step. Maybe we could have a little bit less angles. Let's have 13 angles and take a look in every step of our for loop. So let's make subplot 1, 3, 1, and there let's take a look how our current f looks like, the unit vec. Let's plot unit vec. Image scale unit vec. and axis equal. Then next to it, and yeah, let's put here current unit vector. And then let's show our sinogram. Temp current sinogram. Oh, this should be up there. And this here 3, and let's have here draw now and pause. So now we can see in every iteration. Maybe we can even have here let's put the number unit vector number from number to string I. So we can even see what is it. I think I think we have to have the font size a bit bigger. And let's put also here non-zero elements in A. Okay, let's see how this works. Okay, our first unit vector has value 1 in the first place and zeros otherwise. And here we see the sinogram. It's a little bit like a sine curve, but very poor resolution. And we only have now the first column in our matrix A. So the next one, this moves one step down. Again, we have a sinogram. Now we have 2 columns. So this guy keeps moving as planned over all unit circles, and you see how our matrix A is building up as a sparse matrix. There's a nice structure coming from the geometry of the X-rays. So that's how it's built up. We can do this also in a bit more detail. So we could have J equals 5, let's say, so 32 by 32 matrix. And we could have, why do we have 6 angles? That's so weird, but let's put 33. And let's see what happens now. Why can I not run this? Where is my run button?
It's already running. It's paused the existing.
Ah, that's right. Stop, please stop. Why is it not there? Ah, come on. Ah. Why?
It's somewhere in the background, the window or the process.
I killed the whole thing.
You're a wild man killing things.
Yes,
Oh,
yeah, the process,
really.
that process is gone. So gone.
Just cold-blooded.
Yeah, but now Matlab is not starting.
It's angry with you.
Yeah. Okay. Now the sinogram looks more like a sinogram. And you see, again, our unit vector is moving along. The sinogram is taking the corresponding form, and our beautiful matrix A is again building up column by column, utilizing the ready-made radon.m code. So you see, now we have built a matrix for our measurement So next week, oh, we don't need this now. And next week we will take a closer look of the singular values of this one, take a look of a little set of reconstructions with this, and we will need to build a model for the continuum model, so to avoid the inverse crime. So we shouldn't produce the data with the same matrix we are using for inverting the data. So we need to build some kind of model for the continuum measurement, and we will actually simply do it so that we will compute the so-called continuum measurement with a higher resolution than we use in our matrix A. So that's one way of a little bit avoiding inverse crime. When we measure real data in the lab, then anyway there is no inverse crime because physics itself is acting as our continuum model. But well, we have the matrix thing constructed, so next week let's look more in detail how these matrices are and how the reconstructions look. Thanks.